Hey guys, this starts the lecture series on the periodic table and periodic law. So just remember for these lectures, you'll need the notes that were part of your first worksheet package. And what you can do is you can take them off of that one and add them to the one that you have now. Just so you have the notes and the problems kind of together, but that's up to you. All right, so periodic table, periodic law. You're also going to find it helpful to have a periodic table available to look at as we kind of talk about some stuff. First, though, we want to look at the history of the periodic table. So it was way back in the 1700s that they said, hey, we should start organizing some of the elements we know something about. So Antoine Lavoisier actually developed a list of all the elements that were known at the time. And at that time, there were 33 elements. So he arranged them into 4 categories. He called them the gases, the metals, the nonmetals, and the earths, because they were found in soil and stuff. And that was all well and good until the mid-1800s. There were more discoveries, and so Newlands arranged elements by increasing atomic mass. And when he did that, he noticed that there was a repetition of properties every 8th element. So he created what's known as the law of octaves. If any of you are in music, you know that an octave is broken into eighths. Later in the 1800s, we were still arranging elements by increasing atomic mass, and there was further connection between, hey, if we arrange the elements by atomic mass, the properties, the chemical properties, sort of repeat themselves. So it's just sort of a refinement of that. Mendeleev in the late 1800s is probably the one most credited, so there's my little arrow for that. He's usually considered to be the father of the periodic table because he, although he still arranged elements by increasing atomic mass and demonstrated a connection between the atomic mass and properties, like all the other guys that recently did the same thing, he's the one that's usually credited with the first periodic table or periodic arrangement because he did something unique. He predicted the existence and the chemical properties of undiscovered elements. So he actually left blank spaces in his table for those elements. And then when they were discovered later on, they actually were able to put some of those elements in their proper places. So he took the ideas of others and really ramped it up a notch. And then in the early 1900s, the proton was discovered. So Moseley discovered that atoms contain a unique number of protons and atomic number, and found that if we could tweak that Mendeleev design and arrange by atomic number, then you could actually see the true periodic pattern of properties. And that gives us the periodic table that we have today. So we have the periodic law. The periodic law says that there is a periodic repetition of chemical and physical properties of the elements when they are arranged by increasing atomic number. So the number of protons determines the identity of our element, and when we arrange by atomic number, we get a repetitive pattern of physical and chemical properties. So here's a block from our modern periodic table. We've looked at this a little bit already. We have the atomic number, we have the symbol, we have the name of the element, the atomic mass. Now, our periodic tables in our classroom do not have pictures of the state of matter. We have colors, especially if you look at the one in the front of the room. And so you may just want to take a note of this, that our solids, on the one in the front of the room, the solids are black, the gases are red, and those that are liquids, there aren't very many of those, but the liquids are blue. The one over on the side does it similarly. I think it does the gases a little bit different. So, our modern periodic table, we have groups or families. The groups or families are going to be the columns or the vertical part of the periodic table, that part we look at to determine how many valence electrons something has. So those are groups or families. And then the periods are going to be the rows. And currently there are 7 rows on the periodic table. You have already met the representative elements. Those are the elements that are in the S and the P block, or the elements in groups 1 and 2, the S's, and then 13 through 18. Those are the ones that have P in their electron, end in P in their electron configuration. Since you've done electron configuration, you also already know about the transition elements. So hopefully you recognize that those are the ones in the D block. Types of elements that we're going to find on the periodic table. We're going to have the metals. And if you take a look at your chemistry cruncher, you will notice, you barely may notice it, and you can certainly go over it with a much darker pencil or pen. There is a zigzag stair-step line, and it's on the left side of boron, goes underneath boron, goes between aluminum and silicon, goes underneath silicon, between germanium and arsenic, underneath arsenic, between antimony and tellurium, and then continues a stair-step kind of design. So on your chemistry cruncher periodic table, go ahead and kind of make that a little bit darker, because to the left of that line, except for hydrogen, hydrogen's not a metal, but metals are going to be to the left of that stair-step line. Except for hydrogen, we just put it up there neatly in the periodic table because it only has 1 electron. Some general properties of our metals: they are solid at room temperature with the exception of 1, that's mercury. They're shiny, so they have luster. They can be hammered into sheets, so we say they are malleable. And they can be drawn into wire, so we say they are ductile. They are excellent conductors of heat and electricity. And if you look, statistically speaking, most of the elements on the periodic table are metals. To the right of the stair-step line are the nonmetals, and you can also put hydrogen over there. Hydrogen is a nonmetal. General properties, many of them, but not all, are gases at room temperature. And unlike the metals, they are brittle. They're dull. If they're solids, they're not shiny, they're very dull. And they're very poor conductors of heat and electricity. Now, on either side of the stair-step line, and hopefully you made that a little bit darker on your chemistry cruncher periodic table, except for aluminum. Aluminum is a very metally metal, as you know, if you've seen aluminum foil and stuff too. But the metalloids are kind of cool because they have properties of both metals and nonmetals. So remember, our metals are good conductors of electricity, and our nonmetals are not good conductors of electricity. So you'll find the metalloids, and if you look, silicon's 1, and arsenic is 1, antimony, any of those. A lot of them are used in computer chips or solar cells, or somewhere where you need semiconductors. And that should make sense to you because the metal characteristics would conduct electricity, but the non-metal characteristics would not. So that's how we get our semiconductors. Classifying the elements on the periodic table, certain groups have names. And so in the S block, in the first family or group, group 1 are called the alkali metals. They're in group 1, so they have 1 valence electron. They are all metals. They're very soft, very shiny, very silvery metals. They have a low density. They have a low melting point. They are super duper, uber duper reactive. They are never found in nature. They are so reactive, they can't wait to get rid of that one valence electron. They are the most metallic elements of our metals. Group 2 are called the alkaline earth metals. And they're in group 2, so they have 2 valence electrons. They're a little more dense, they're stronger, and they're harder than the metals that are in group 1. They're less reactive than group 1, but they're still too reactive to be found pure in nature. Going over to the P block in group 13, and then to group 18. Now, our stair-step line occurs in this space. So some of those elements are metals, some of those elements are nonmetals, and some of those elements are metalloids. So if they're over there in the P block and they're metals, they tend to be harder and more dense than the S block metals, but they're softer and less dense than the D block metals. Metalloids are very brittle solids, because you remember they have both characteristics of both metals and nonmetals. 2 noteworthy nonmetal families are group 17. Those are called our halogens. And you remember the last digit tells us the valence electron. So they have 7 valence electrons. So guess what? They are super reactive. They are the most reactive. Now notice they only need 1 electron. So there is some other family and group on the periodic table that's dying to give an electron away. So they react super well with the alkali metals. And then group 18, we've looked at when we've done electron dot configurations, and we do a noble gas configuration. Well, these are our noble gases. They have 8 valence electrons, and they're generally non-reactive. They don't really form compounds. So another term that's used for them is we say that they are inert. They're also known as the inert gases. In the D block, that's going to be groups 3 through 12. These are known as the transition metals, and they are metals. They have typical metallic properties. They conduct heat and electricity well. They're malleable. They're ductile. Now, their group number actually comes from if you add up their outermost S and D electrons, you'll actually get to their group number. So pick one, do its electron configuration, and you'll see that that's true. If you go down to the F block, your Chemistry Cruncher periodic table tells you that that first row are called the lanthanides, or the lanthanide series, primarily because the first element in there is lanthanum, and they are shiny metals. They react a lot like the transition metals. And then the second row you'll see on your periodic table from your Chemistry Cruncher, they are called the actinides. The second row are the actinides. And all of the actinides are radioactive, and most of them are actually man-made. So this concludes our lecture. So what I want you to do right now is to stop the video. I want you to scan this QR code and answer the questions that will verify that you watched the video and took the notes. After this, you'll work on the getting to know the periodic table problems. And as always, if you have any questions, just let me know. Thanks, guys.